Sinusoidal and cosinusoidal waves are a large part of our everyday life, yet for the most part are an invisible mechanism that is constantly working around the clock. But first, what are sine and cosine waves? Both of these waves are derived from the unit circle, a circle for which its radius is 1 radian and has a circumference of 2 pi radians with 360 degrees. Imagine a graph where the range is -1, 1, and the domain is -2 pi and 2 pi. Both the sine and cosine functions will graph a wave with an amplitude of 1 and the period of 2 pi as based on the unit circle. Now given an angle that creates a ray starting from the origin that then intersects the circumference of the circle, the intersection will be given a point, for which of said point's coordinates will be used to determine what cosine and sine values of said angle will be given. A sine wave is the plotting of the y value of the coordinate of the point of a given angle in the y-axis of our imaginary graph, where the x-axis represents each angle of the unit circle and the y-axis are the given values from sine and cosine. A period, or full repetition of the unit circle, is completed in 2 pi and forms our wave. Cosine waves are the same, except use the x-coordinate of the point to then be graphed in the y-axis. As the x values, or angles, increase, a wave will be formed that will infinitely repeat and can be expressed in the equation a times function times b times x minus c plus d, where the function can be either the sine or cosine function. Within this equation, a represents the amplitude, b represents the period by dividing the standard period of 2 pi by the given value of b, c represents a horizontal shift or phase shift, and d represents a vertical shift. Within real life, this equation can express many purposes, as a can be used to express the increase or decrease of the intensity of a given mechanism, b their frequency or speed as then measured in hertz, while the translations of the wave can be used with c, as they can be used for constructive or destructive interference, and d to increase range by being at a higher altitude. The first example of waves being a large part of our life is evident in sound waves. Sound is a vibration of a medium that is then transferred to our eardrums to be recognized by our brain as a sound, and it is commonly depicted in the movement of waves. When applying our equation of a times sine times b times x minus c plus d, the characteristics of sounds that are altered are pitch, that is measured in hertz, and intensity or loudness that is measured in decibels. A and c in our equation can be used to amplify the loudness of the sound. A increases the amplitude or strength of the sound. An example of this is concert speakers vibrate air at such strengths to produce a louder sound that can traverse large distances. C can be used to create constructive or destructive interference. This can commonly be seen in noise-canceling headphones, as external microphones repeat outside noise back to the outside environment with a phase shift to cause destructive interference. On the other hand, B, or a change in period, can be used to increase the frequency or pitch of the sound. As sound moves at a constant speed in the air, the faster the vibrations are, or the more waves are transferred to the eardrum in a given time frame, the higher the pitch will be. A great example of this is with any type of string instrument, as the vibrations of a thicker and heavier string will produce slower waves, thus a lower note, whilst a thin and light string will produce a faster and more rapid wave, producing a higher pitch. Similarly, when you slow down an audio that may have a higher frequency, the playback speed reduces the frequency of the audio to then produce a lower tone. The last example is light waves, which may be confusing, as many believe that light exists as rays of photons that bounce off of objects and eventually reach our eyes. This is true, however, light also exists as waves and can be seen with the use of two polarizing lenses. Polarizing lenses only allow light waves of a certain orientation to pass through. Upon being in the same orientation, the lenses may both let upright light waves pass through, and thus a dimmer picture is formed through the lenses. Yet, a rotation of one of the lenses 90 degrees results in neither upright nor flat orientated waves being able to pass through, resulting in a black picture as no light can display the image through the lenses. Then how can we use our equation of a times sine times b times x minus c plus d to represent the characteristics of light? An increase in A results in an increase in the intensity of the light, thus making it more brighter and/or a color more vibrant. This can be commonly seen with spotlights, as an abundance of waves results in an increased strength of light waves due to constructive interference. An increase in B alters the color of the light. Within the visible light spectrum, red light has the slowest frequency and purple has the fastest. From red to purple in order of the rainbow, the frequency increases. Since light is essentially everywhere and its output is in sync, C does not heavily affect light, as although there are sources, the sources emit light that only goes through constructive interference. This can be seen when red and blue light merge to form magenta light. On the other hand, D stands as sources of light. This can be seen in the sun, the moon, street lamps, television, flashlights, and many other things that have become essential to our everyday life. This is only the surface of what waves provide for humanity every day. This video is the minimum of waves in everyday life, as numerous other waves exist and are complex in their own way. As technology further develops, the use of waves may become more complex and provide further information.